Hi, my name is Sandeep Kumar. I'm a PhD student at Indian Institute of Technology, Delhi, India. Today, I'll be talking about our work on efficient management of page table pages for a tiered memory system. This work was done during an internship at Intel Labs, India. Here is an outline of the talk. First, I will discuss some relevant background, followed by the motivation for the paper. Then, I will talk about some of the observations for a tiered memory system. After this, I will discuss the proposed techniques in the paper. Finally, I will conclude with some evaluation results. We will start with the background. This is how a traditional CPU memory system works. The CPU accesses the data via system bus when required. Intel Optane persistent memory sits on the same system bus and is byte addressable. The Optane cards are also DDR4 compatible and fits into the standard DIMM slots. Optane memory can be configured in two different settings. In the first setting, DRAM acts as a cache and Optane as the main memory. This is completely managed by the hardware. In the second setting, DRAM and Optane are presented as a unified byte addressable memory. Here, the data placement is under the control of the system software. This allows for an opportunity to efficiently manage the data. In this setting, the Optane memory shows up as a CPU-less pneumonodes in the operating system. We use this setting in the paper. Here is a brief comparison of DRAM and Optane. DRAM has a relatively low access latency, however, also a low capacity compared to Optane. On the other hand, Optane has a high access latency, but also a high storage capacity, along with the persistence guarantees that it comes. Ideally, we would like to place hot data on DRAM and cold data on Optane, mainly due to the difference in the access latencies. When we say data, we mean both the user and the kernel data. Many prior works have focused on the placement of user data. However, the kernel data has not been looked upon. The main aim of this paper is the optimal placement of page table pages. There is another recent work that focuses on the placement of kernel objects. Let us now discuss a page table. To access the physical pages of a process, we need to convert the virtual address generated by the CPU to a physical address. The physical to virtual address mappings are stored in the page table. To reduce the cost of a lookup, a page table is organized as a radix tree. To find a mapping, we start at the root, that is the PGT. Then using the bits in the virtual address, we move down the tree till we reach the last level that contains the final mapping. Please note in the worst case, to access a data page, we may need to access 4 levels of the page table. That is, a single memory access can trigger 4 other memory accesses for the page table. Hence, optimizing the access to a page table is even more crucial. Furthermore, the size of a page table depends on the physical data accessed by the application. For example, to map 2 terabytes of data pages, we need 4 gigabytes of page table pages. Now, we will discuss the motivation for the paper. First, we will discuss two kernel memory allocation policies. The first one is called a first trust policy. In this case, a CPU will prefer to allocate on a NUMA node which is closest to itself. This ensures a quick access to data. However, as, as Optane shows up as CPU-less NUMA node, it is always remote to a CPU, and hence a CPU will prefer first to allocate on DRAM, then if required on Optane. The second allocation policy is called an interleaved memory allocation policy. In this case, a CPU will allocate data in a round-robin fashion in all the NEMA nodes. This ensures a parallel access to the data. As already mentioned, Optane has a high access latency. Also, in the worst case, we may have to access a page table 4 times to access a data page. Hence, we would like to ensure that the page table is present in the low latency DRAM. However, the current page table allocation policy does not take this into account, and the page table pages can end up in Optane even when there is memory in DRAM. We discussed two such cases. The first case is when interleaved memory policy is used. Let us assume that these are free data pages. In the interleaved memory allocation policy, the kernel allocates the data on all NEMA nodes in a round-robin fashion. This policy is also applied to the allocation of page table pages. Hence, a page table page can end up in Optane even when DRAM is free. The second case is related to how kernel handles the migration of pages. We will show this by an example. Again, assume that these are free pages. Here, first touch memory allocation policy is used. When process A starts executing, all of its memory allocation happens from DRAM, as it's free. Let us assume that it completely fills up the DRAM. When another process B arrives, as there is no space on DRAM, all of its memory allocation, including the page table, happens from the Optane. Now let us assume that process A finishes its task and quits. This frees up the DRAM. In this case, the kernel will migrate all the data pages of process B to DRAM. However, migration of page table pages are not supported as they are part of kernel data structure, and hence they are not migrated. The page table pages are stuck in Optane even when there is free memory in DRAM. They will be reclaimed only in two cases: if the process frees the data page mapped by those page table pages, or the application quits. To summarize, a page table page can end up in Optane even if there is free space on DRAM. As a page table, because a page table allocation follows the data page allocation policies. Furthermore, once it is allocated in Optane, it cannot be migrated to DRAM, even if there is space in DRAM. In this paper, we deal with both of these issues. Now we will discuss some of our observations in a tiered memory system. These observations further warrants the need of a better page table management system. In every system, TLB is a small cache that contains virtual address to physical address mappings. In the event of a TLB miss, we need to do a page table walk to fetch the mapping from the corresponding page table. The size of a TLB is small and does not provide much coverage in terms of amount of memory access. Hence, for large memory applications such as there will be the TLB miss rate will be high, and consequently the number of page walks required is also high. Here, in this case, while populating 1 terabyte of data, we can see that till the page table pages are in DRAM, a page table walk incurs nominal latency. However, as soon as the data spills on Optane, the page walk latency increases manifold. Hence, page table placement is crucial. Before going to gradient techniques, we want to discuss a naive solution for the problems mentioned till now. In a simple solution, the complete page table can be pinned or binded to DRAM. This is called a bind-all policy. It ensures that all the page table access happens from DRAM. However, this results in some pathological cases. We will discuss these cases next. In bind all, as all page table pages must be allocated from DRAM, suppose we are allocating memory more than DRAM. Initially, all the data and page table pages allocation happens from DRAM. However, once the DRAM is full, the data allocation spills over to Optane. However, in this setting, page table allocations are not allowed to spill over to Optane. Hence, the kernel tries hard to make space on DRAM for these page table pages. It reclaims pages on DRAM. This increases the latency of the page table allocation. Eventually, the kernel fails to accommodate any more page table pages in DRAM, and the application crashes with an out-of-memory error, even when there are few pages in the Optane. This technique was proposed by Linux kernel developers but was not accepted in the mainline kernel. Now, we will discuss the variant techniques. Our techniques are based on a crucial observation. As mentioned earlier, for a 2 terabyte of data pages, we will typically need 4 gigabytes of page table pages, assuming we are using a 4-level page table. However, more than 99% of that 4 gigabytes is present in the last level or the leaf level of the page table. The high levels of the page table, that is the top three levels, only uses around 7 megabytes. Based on our previous observation, we pin or bind the high levels of the page table, that is the top three levels, in DRAM. This guarantees that three accesses, that is 75% of all page table accesses, will be from DRAM. This comes at a cost of 0.2% of the page table size. However, this setup is not complete, as the last level or the leaf level, which constitutes the majority of the page table, can still end up in Octane. This leaves us with the original problem again. To solve the issue of the last level or leaf level pages of page table ending up in Optane, along with the pinning and binding of the high levels of the page table pages, we transparently enable the migration of the leaf level page table. This ensures that even if a page table page allocation spills to Optane, it will not be stuck there, and it can be brought to DRAM as soon as the memory pressure under DRAM reduces. Hence, with a very small space overhead, we ensure that 75% of accesses are from DRAM, and with migration enabled, hot leaf level pages can be migrated from Optane to DRAM if required. Now, we will discuss when exactly we migrate a page table page. For this purpose, we track the migration of data pages across NEMA nodes. This information is given to the weighted algorithm, and that decides whether the corresponding page table pages are also to be migrated. We achieve a page table migration practically for free by piggybacking on the data page migrations. We do not use any additional data structure nor any additional tracking mechanism for this purpose. Also, we are independent of data page migration mechanisms. Now, we will discuss some of the evaluation results. This is how our evaluation system is configured. We have a two-socket machine where each socket has one DRAM module and one Optane module. In the operating system, this shows up as four NEMA nodes, with node 0 and node 1 as CPU and DRAM nodes, while node 2 and node 3 are CPU-less Optane nodes. In case of bind high, where we pin or bind the high levels of a page table in the DRAM, improves the walk latency by 23%. This is mainly because now during a page table walk, 75% of page table walks are guaranteed to be from DRAM, irrespective of the data page allocation policy selected. When we enable the migration along with the high-level page table pinning. In a full system run, when a single application is using all the resource, the performance of the application improves by 20%. This is mainly due to the reduction in walk cycles, which in turn also reduces the stall cycles due to a quick virtual address to physical address mapping resolution. In a multi-tenant environment, the average performance improvement is 50%. This is mainly due to more opportunities of a page table migration across the different NEMA nodes. In conclusion, we show that the placement of a page table in a tiered memory system is crucial. Naive solution, such as pinning the page table in the DRAM, will not solve the challenge, will not solve the issues. We leverage the page table structure to devise simple yet efficient solutions. We use a different policy. We use different policies for different part of page table to ensure an efficient page table walk. We achieve page table migration with minimal overhead by piggybacking on the data page migration scheme. With that, I would like to thank our listeners and we are open for questions. Thank you.